So we got the terminology north and south. We understand that the magnetic field lines go from north to south, and we know that we can map it using a compass. We also understand that if the charges are at rest, they're not going to be affected by the magnetic field. If the charges are moving parallel to the magnetic field, once again, nothing is going to happen. Across the magnetic field, they will get deflected by a force, which is going to be 90 degrees to the motion of the charge. Right-hand rule number one is going to give us the direction of that force. So that's the only purpose that it serves. And then this is an example that we looked at. It's not a big deal. All right, so if the current is coming out of the page, the magnetic field is going to wrap itself around the current. Okay, so this question doesn't belong in there, so let's move forward. We'll get back to the same question. Earth's magnetic field is going to protect us because the charges going across the magnetic field will become deflected at right angles to their motion, which means that if the charge is moving in this direction, if the force is in this direction, it causes a circular motion. So deflection is going to happen in the form of a circle, so they will just wrap themselves around the magnetic field and driven into the atmosphere at some point. All right, so magneto-hydrodynamic propulsion system is an example of the right-hand rule number one. I'm not going to worry about the details right now. All right, the formula used for the right-hand rule number one is this formula. All right, so this one is a cross product. So it's going to be V cross B is going to give you F. All right, so this is the scalar form of the same formula that we're looking at. All right, question number 4, we haven't done it yet. It's today's lecture. 15, we haven't done it yet. All right, 16, we haven't done it yet. 17, ignore it. All right, move forward, move forward. What else did we do? Magnetic torque, no. All right, so Ørsted, what did they discover? They discovered that the current is what caused magnetism. All right, so in order to figure out the direction of the magnetic field, we use the right-hand rule number 2. Line up your thumb in the direction of the wire. If the current is going up, thumb is lined up, the fingers will curl in the direction of the magnetic field, and that's it. Obviously, if the current is coming out of the page, magnetic field is going to wrap in the counterclockwise direction. Reverse the direction of the current, the magnetic field is going to wrap itself in the clockwise direction. All right, so we haven't discussed any formulas at this point regarding that. All right, moving forward. All right, so we talked about an electromagnet. It's just a current loop. Current is what generates magnetic field. All right, so if you want to turn this into a magnet, increase the number of turns. All right, turn it into a coil, and then place an iron core in the middle, it becomes magnetized. That's it. All right, so you got your electromagnet. Henry is the guy who's responsible for the invention of an electromagnet. And Ørsted is the guy who discovered that the electricity generates magnetism. Is it possible to wipe out credit cards using regular magnets? Not today, it's not that easy. You have to use extremely strong magnets for something like that. All right, so the biggest question is, are there magnetic charges? Are there magnetic monopoles? You take a magnet and break it into smaller and smaller pieces. It doesn't matter how small the pieces are. Magnets will always be magnetized, which means that they will always have a north and a south. All right, so all of a sudden the question is, do we have any magnetic monopoles? According to classical physics, the answer to that question is absolutely not. That's what the classical physics says. Because what generates magnetism is the orbital motion of these charges. And according to classical physics, the electron orbits the nucleus, like the way the planets orbit the sun. So the motion of the charges is known as current. And if there's current, there's magnetism. That's it. So which means that the atoms are magnetic, where atoms are small magnets. All right, so, and this brings us to the next point. Iron is very easily magnetizable, for example. The reason is because it contains regions within which the atoms are already facing the same direction. If the atoms are facing the same direction, those small regions are magnetized. So you can get the entire atom to become magnetized by using an external magnet. So these little small regions known as domains end up pointing in the same direction. So how does heating destroy magnetism? Heating is simply on the atomic scale, which means that you're causing random vibration and rotational motion, which means that the atoms start facing at random directions. The magnetic field being a vector field, it can be reinforced, or it can be canceled. So the overall effect diminishes, eventually cancels out. So is it possible there's magnetic field to be generated by surface currents? The answer to that question is no. Surface of the Earth is negatively charged. By the spin motion of the Earth, you know, you got surface currents. You know, Earth is spinning on its axis roughly about 1,000 miles per hour. It would cause a magnetic field in the opposite direction of the Earth's magnetic field. So this explanation will go. And the next thing that we did, we looked at the core spinning in the direction of the spin of the Earth. Once again, you have the same problem. Magnetic field would be pointing in the wrong direction. First, to be able to get the magnetic field to point in the correct direction, you have to have the core spinning in the opposite direction of the spin of the Earth, and against the friction of the Earth and given the pressures and all that stuff. You cannot justify that kind of spin. All right, so all of a sudden it becomes a mystery. So what do we know about the Earth's magnetic field? We know that the currents cause the Earth's magnetic field. And we also understand that there's molten metals, charged metals are flowing every which direction. Those are known as conduction currents because of heat. We believe that that's by and large responsible for the Earth's magnetic field, but we don't have any direct evidence for that is there. All right, so that's how it is. All right, so this was a real fast review of everything that we discussed so far. Okay, so let's just build on what we already know. We're going to talk about the electric motors. Does anybody know how an electric motor works? Somebody, anybody?
Kinda.
Okay, explain. Just keep it short.
Electromagnets.
That was really nice. All right, here's how points. That was very insightful. So now I know how to build one. All right, so Ian, what do you do with it? I mean, how does it work? Okay, so let me help you out. You got a spinning coil inside a magnetic field. That's it. All right, that's it. Just get a coil. Remember the he's right. It's like an electromagnet which doesn't have a iron core in the middle. Literally, electromagnet. You got this coil. The only thing you have to do is just run current through it inside an external magnetic field. So magically it spins. That's it. All right, so the question is, how does the magic happen? All right, so we'll find out. All right, Ian, that was very insightful. Let's move forward. All right, so boom, 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 north and the south pole. So are there any monopoles in case there's a test question? The short answer is going to be C. Go for C. If C is not the right answer, do an upgrade. All right, so let's move forward. So what we have, compass is magnet on a pivot. So notice that always going to line itself up along the direction of the Earth's magnetic field or along the direction of the external magnetic field, which is a good thing. Why? So that you can actually map the magnetic field. Earth's magnetic field, obviously, we discussed what it is. Obviously, there's a magnetic field. It's a strong magnetic field, strong enough, I'm just going to say, in order to protect us from charged particles. So what would happen if we did not have a magnetic field of any sort? Okay, let's talk about life without a magnetic field. What would happen to the Earth? Forget us. All right, the cancer risk are going to go up, this and that. I get that. Okay, what would happen to the Earth if we did not have a magnetic field? Any ideas, any suggestions? Let's have somewhat of a meaningful discussion at this point. What would happen to life as we know it on Earth? Or what would happen to Earth without the proper magnetic protection? All right, guys, just feel free to jump in if you have a theory. Right or wrong, it's not a big deal. Give me a starting point.
Probably never would have been much life, right?
Okay, well, I agree with you on that. Why not?
Because of the radiation.
Okay, I was thinking that that's what you were going to say. I'll give you 5 points. Yeah, because of the radiation eventually. It would probably kill life as we know it, but there's a bigger danger if there's no magnetism. What would happen to the atmosphere, guys? Yeah, it would knock. Yeah, it would literally, the incoming particles, and these are fast-moving particles, it would just knock off the molecules making up the atmosphere. Gradually, we'll lose the atmosphere. That would be a huge problem. It is believed that that's what happened to Mars. All right, so for whatever reason, the dynamo, which was responsible for generating Mars's magnetic field, it just stopped working. And then, obviously, Mars ended up losing its atmosphere, much of it. All right, so that's what would have happened. So the Earth's magnetic field protects us from these charged particles. Also, it protects the atmosphere, obviously. Without it, we would have lost, I'd say, like 99% of the atmosphere. All right, do we have any magnetic monopoles? The answer to that question is no, because you can trace the magnetism all the way down to atoms. The atoms are magnetic for the reasons that we discussed previously. And then we know that the like poles will repel, non-like poles will attract each other. All right, and then we discussed something about the discovery of the electron. So you got this electron beam, or some kind of a beam, which is responsive to the external magnetic field. Okay, by looking at the direction of the deflection, it was determined that this beam was composed of electrons. And we understand that if the charges are moving parallel to the magnetic field, nothing happens. They will experience a force upon going across the magnetic field. The direction of the force can be determined by using the right-hand rule, and you apply the left hand if it's a negatively charged particle. You need to remember. All right, so this is the right-hand rule of number 1 from calculus. And this is the one that I usually use because it's more practical for, I use, joke aside, guys. I mean, you do, your thumb is going this way, the fingers are going that way. Your thumb is in the direction of the velocity vector, the fingers in the direction of the magnetic field. Palm points in the direction of the force. And we literally used to put the finger up when we were doing that sort of stuff. And for politically correct reasons, obviously now everything is flattened. All right, and you think I'm kidding, I'm not. All right. And the particles going across the magnetic field will become deflected. And if a particle finds itself in a constant magnetic field region, it's going to go in circular motion. All right, speaking of going in circular motion, let's check to see if this thing is working. You can actually figure out the mass of an electron Let me check to see if there are numbers here that we can play with. You can't. You can see the electron beam here. So this is really neat. All right. All right, so let's work on problem number 3. This one is an electron beam similar to what we were just looking at. So understand, we know the kinetic energy of this one. This is 22.5 eV electron volts. This is at a uniform magnetic field. It's actually fairly weak. It's not that bad. It's 10 to the minus 4. And then what's the radius of each electron's path? What's the frequency of the circulating electron? And what's the period of revolution? All right. Once again, I'd like to make things interesting for myself. I don't like solving problems step by step like that. And normally, if this was in person, I would have, your test question would have been either figure out the frequency or the period given this information. All right, so that's what I want to do. Which one is more interesting? Frequency or the period? I'd say period is a little bit more interesting. So what's a period? Period is the time it takes for the electron to actually complete the cycle. All right, if it's this starting point, how long would it take for the electron to get back to the same point? All right, let's go after that. So somehow magically we know the kinetic energy of the electron. How do we know what the kinetic energy of the electron is? And we understand the strength of the magnetic field. All right, so before we actually even attempt at this problem, let me ask you this question. How do we know what the energy of the electron is? Where would you get it from normally? Don't say it because it's stated in the problem, I'll kill you. In real life, where would you get that from? 22.5 eV.
Did you figure it out if you're like running it through a capacitor or an electrode?
Right, the electron gun, right? Exactly, yeah. You know the voltage difference between the place, and that's it, guys. And then you place an electron, that's the energy. So, which means that I'm looking at it, it's the potential difference between the places 22.5 volts in this case. So, place an electron there, and now you got 22.5 eV. All right, so electron gun, you're just going to project these electrons into that region with that amount of energy. All right, so external magnetic field is set to that value. So let's figure out the period of this motion. All right, so this is problem number 3. Problem number 3. This would be an interesting problem to do. All right, let me just get the numbers in first. Problem number 3.